Hello, my name is Strzebonski, and I'll be talking about functions, singularities, and their applications. So in Mathematica 11, we have built-in knowledge about singularities and branch cuts of mathematical functions. So basically, previous versions of Mathematica, of course, needed this knowledge, and various functions had their own partial implementation of the thing. So many functions needs to answer a question like, is the input a continuous function, or where are the discontinuities of the input, or is the input an analytic function? So, but here with Mathematica 11, we have unified the knowledge so that it's in one place and all the functions access it from the same place, and we sort of try to make it as complete as we can. So it's at least as complete as functions.wolfram.com knowledge. So here it is. So what kind of information do we store? So is the function locally analytic, meaning analytic in some neighborhood of the point? What is the location of branch cuts of the function? What is the location of definition boundaries? So that would be boundaries of the domain of the function, boundaries of the set of real arguments for which the function is real valued. So if we are looking at the real domain of the function, so where the function becomes not real. And boundaries of piecewise cases if this is a piecewise function. Another information is location of poles, essential singularities, and branch points. For some functions, it's important that we distinguish between those. For others, it's not. So this general knowledge base does make a distinction. So we will describe the singularity, or currently so one thing I need to mention, this function is not yet packaged as user function. So as you can see here, it's simplified context function that gives not quite completely designed output, but it's what's used internally, and in the next version we will have better packaged design system context function for this. So I'll describe what we have right now. So what we keep in the knowledge base is description of singularities as pairs equation and condition. So that the solution set of equation and condition includes the singularity set. It may be strict inclusion. So basically we do not have information about exact location of singularities. We may have to give a larger set. That's because we want to propagate the description through function composition, and the exact location of singularities may not propagate, since, for instance, poles from different parts of the expression may cancel, or branch cuts may cancel, or through a composition, a pole may become an essential singularity, or may not, and we don't have this detailed information because we want to collect this information very fast. So we are not really computing anything. We are collecting information syntactically and basically propagating it through this formula, simple formula. It's so singularity of a composition of function f with an argument function will be singularity of f with variables replaced by those functions, plus singularities of the argument functions. That means we can really fast collect this information just by knowing the information about every named built-in function. So as I said here, poles may become essential singularities or removable singularities of the composed function. So function singularities would assume worst case scenario, meaning that if we say that there may be an essential singularity, it means there is an essential singularity or a pole or a removable singularity. And if we say there is a pole, then it means there may be a pole or there may be a removable singularity there. But we always give a set which includes all singularities. So here is the current output of this function. Basically, you get least description of branch cuts, domain boundaries. This comes from the inverse elliptic norm Q. Then this will be poles, essential singularities, and branch points. So what are the current applications? For instance, those are applied in visualization. There will be 2 visualization talks after my talk. There will probably more about it. So for instance, with Mathematica 10, Plot didn't know about the singularities of tangent, and that's why we were getting these vertical lines. Now it does have the information, and there are no vertical lines, so the plot looks much nicer. Same for gamma functions. Again, we had vertical lines for singularities, and in Mathematica 11, the lines are gone. Here's a function composition. So you can see the old version, again, had vertical lines. The new version can figure out the singularities of function composition, and we got a nicer picture. Yes?
How are you controlling the versions? One of the lines is mathematical and the other is mathematical.
I typed in manually, evaluator goes to named kernel in those cells that do not use the Mathematica 11. And here's a tree picture. So again, there was a singularity here, and we sort of get this wall here. And if plot 3D knows where the singularities are, we get much nicer picture. Okay, so now solving univariate transcendental equation, another quite different area that also needed the information about function singularity, and it did have some information before, but it was not as complete as it is now. So reduce and related function. Find roots of univariate holomorphic function in a complex rectangle using the following heuristics. We first find bignum approximation of the roots using numerical method. Then we use interval arithmetic for elementary functions, or significance arithmetic for non-elementary functions, because we don't have interval arithmetic for those, and a criterion based on the Rouchet theorem to prove the existence of and multiplicities of roots. So then we have proven that the roots are where we found them, where the numerical method has found them. And then we need to prove that we have found all the roots. The numerical method might have or might not have found all the roots. So to do this, we need to compute the winding number of the function along the boundary of the rectangle. And this way, we will know how many roots counted with multiplicities are inside. And if this number agrees with the number of roots that we have found, we know that we have solved the problem. So, but of course, to do this, we first need to know that the function is holomorphic in the rectangle. So that's where the singularity information enters. And so, for instance, here's a holomorphic function. And we get the solution. We get a warning since, well, the warning means exactly what it says. Solve needed to use numeric integration to compute the winding number. So we can compute the winding number using interval arithmetic for elementary functions. For non-elementary functions, we need to use numeric integration. But it's almost proven that we have the correct number of solutions. It's really unlikely that numeric integration didn't give the first digit correct, because it needs to tell between 5 and 4 or 6 roots here. So. And here's a picture. We can see that we have found all the 5 roots. These are zeros or really imaginary parts, so where they intersect are the roots. Okay, and now meromorphic functions. This is something that's new in version 11. So version 10 and earlier had some knowledge about where the function is holomorphic. So for some holomorphic functions, it will work. We didn't have any information for meromorphic function, the location of poles. So that wouldn't work in version 10. So we have a function that's meromorphic, and we can find the roots of it. Now there are no messages because this was an elementary function. So the additional information that we need for meromorphic function is the location of roots. So we get equations of poles. We get equations that need to be satisfied by the poles. We solve the equations, then we compute the multiplicity of the pole at the solution, and this way, and knowing the winding number, we can compute the number of roots. And here's the picture. Again, these 4 roots are intersection points. At intersection points are roots, and this you can see that it's not quite intersecting. There is a little fuzz here because that's the pole. That's where the real part goes off to infinity. So there isn't really intersection in these 2 points. And here's what it looks like. If we plot the absolute value of the function, you can see that it has 2 poles here, and the roots are sort of underneath here. These are the minima of the absolute value. Okay, root counting. So that's pretty much the same as finding roots, except we don't really need to find the roots. We just need to count them, so we need to compute the winding. We need to compute the winding number, and we need to know that the function is holomorphic, or that it's a meromorphic function, and we need to then locate the poles and find the pole multiplicity. Then we can count the roots. So here's an example, an elementary function. And it takes a while to count the roots, because that's with this exponential term and cube term inside the tangent, it will have many roots. Yes?
It sounds like you need a winding number function.
Yes.
Okay.
And I do have a winding number function in an internal context, which you might export it or not. So the winding number function, if it's an elementary function, it uses the interval arithmetic. And we also have complex interval arithmetic also in a hidden context. And here's a picture. So this function has a lot of spikes. Those spikes are poles that we need to count. The poles come from the tangent function, and the roots are the spikes underneath. So there should be 71 of them. I don't know if the numerical method got all of them here. And here's a special function. So this was really fast. The numeric integration here, and we see that there are 11 roots. And where the 11 roots are and intersection, but it's root counting, so I didn't mark the roots because we haven't found them. Just counted that there is 11 of them. And periodic function. So count roots uses function period. So that's another function that we had for a few versions now that can find data on the periodicity of a given function. So if we recognize that the function is periodic, then we really need to count the roots in one period and in the remainder of the period. So we didn't really have to sort of count the winding number of 6 billion here. We just needed to count it in one period and to count the number of periods and count the remainder, sort of modulo pi of the length of this interval. And this is something that would actually take a while, because evaluation of Jacobi CD is not that fast. So, but in 69 seconds we can compute there is 3, I think, quintillion of roots in this rectangle. So. Okay, univariate optimization, another area where we need data on function singularities. So if we want to optimize a univariate function for which we can symbolically compute derivative, we not only need to find the roots of the derivative, but the derivative is computed in generic sense, meaning that it may have discontinuities, and we need to find those discontinuities. And also the function may not be always real valued, so we need to find the endpoints of the real valuedness domain of the function. So here's the first example. We'll have a maximum at a regular point of a function. So as you can see, I constructed the function with a function component that's a piecewise function, so it's not function that would always have derivative. And here's the solution in terms of transcendental root objects, but it's an exact number. And here's the plot of the function. You can see the function had a few discontinuities, and here the derivative had discontinuity, but the maximum happens to be at the zero of the derivative. But if we slightly change the function, so if you look at the function here, I just added a constant there, multiplied the first term by constant, and we compute the maximum here. Now the maximum is at 0, and that's the point where derivative is discontinuous, where the maximum occurs. Here's another example. So this function looks analytic, but as you will see on the plot that it's not quite the case because of the arc cosine, which has branch points where sine is 1 and -1. So that's what the function looks like, and the maximum is actually at one of those points where the derivative is discontinuous. And again, the same function with a constant changed, which would be able. Okay, I added the constant 2 here, and this is to illustrate that we also need to know where the endpoints of the real valuedness domains are. We get the solution, and the solution happens to be at the endpoint of real valuedness domain. The function is not real valued between those pieces of the graph. Okay, limit computation. So this is sort of trivial criterion definition. The function is continuous at C, then the limit of the function at point C is equal to the value. But before we had the information about where the function is continuous, limit was not using this information because it didn't have it, so it was computing series of whatever function it got. And if the function is complicated, then the computation of series takes a long time. For instance, if we take nested cosine, do it 17 times, then computation of limit of this at 0 takes 119,000 seconds in version 11, actually, because this is something that was implemented after version 11. So this will come in the next version. So, and after the criterion, cosine is of course continuous at 0. So we get like 0.3 millisecond for the same thing, which is the highest measured speedup that I was able to ever do, 3.9 billion.
So, what if you went 18?
Well, I tried it. I let it run for a week, didn't finish. So, And with function singularities, we can go to about 20,000. It's still fast, so the limit here is not the speed, the limitation here. The limitation is the stack size. After about 100, the stack crashes, and and we cannot replace. So the problem is replacing x with 0 in the function using replace all, because it builds too high stack and it crashes. So. And here is, so if we nest it a million times, we still can pretty quickly figure out that the function is continuous. And next example, so what about if there are any singularities? So we use tangent instead of cosine. So as you can see, I needed somewhat smaller number of nesting, and now it takes measurable time. It takes 1 second to compute for 100 times nested tangent. And the limitation here, again, why we cannot do too much more is the evaluation of numerical evaluation of the conditions. So we produce a bunch of conditions here. You can see the leaf count. So for instance, if we nest tangent 10,000 times, we get a lot of conditions, 10,000 conditions. They become larger and larger. The leaf count of the condition is 50 million. And replacing values in those conditions takes time. And here's an example of sort of random composition of special functions. If I type it randomly, then it's very likely that the point will be a point of continuity, and we can get limit really fast. And that's now it evaluates version 11, so it doesn't have the criterion for continuity, and it took 3 seconds to compute the same thing. Okay, so let me finish with something which I don't even have in the development version. So, but it's something that also can make use of function singularities, computing various types of integrals using the antiderivative. So we can compute the regular Riemann integral using Newton-Leibniz theorem. To do this, we need to find all the singularities that are along the integration path and compute limits of the singularities. Also, if we want to compute Cauchy principal value integral, again, we need the singularities along the integration path, and now we compute symmetrical limits. So it's also a combination of computing singularities and computing limits, and of course, computing the antiderivative. And for Hadamard finite part integrals, we need to compute series around singularities and remove the non-convergent terms. So again, that's where function singularities will be used. There is some more difficulty to it, especially if there are symbolic parameters present. We need to figure out under which conditions on symbolic parameters which singularities are in the integration path. So that's solving somewhat difficult geometric problem there. But it's something that will use the knowledge of function singularities in particular. So this is all I had. Thank you.